Hello, can you all hear me? You can unmute Finley, just so we can know if we can hear you. Let me share my screen. Sorry for running a bit late. Can one of you try to unmute and say something just so I can make sure that I can hear you?
We love you, Joshy.
Yes, yeah, I can hear you. Cool. So I guess before I get started, are there any questions about anything relating to the midterm exam? No? Okay. So these slides are available on Canvas under Exam1 resources or in the folder for the discussion slides. The objectives for today are that we're going to talk about the trees and traversals, balanced trees, and heaps and priority queues. For the trees and traversals, primarily you just need to, remember the structure of a tree node and that it has children. It is possible to have an in-array tree that has n number of children. An example of that would be like a B tree or B plus tree. And when you are coding like for pseudocode on your exam, you can use any sort of node class. Like if it's a binary tree, for example, you can just assume that it has like a value left, right. Like you don't have to create the class itself. So yeah, any questions about that? I would recommend, there are going to be, I think, 3 like free response coding questions on the exam. So I recommend looking at the pseudocode slides again, just so you are aware of how to do that. As for the tree traversals, the primary ones that we've talked about are pre-order, in-order, and post-order. So I would know all of these traversals and like how to perform each of them and like the order in which the nodes are visited. These types of tree traversals are an example of a depth first search. So primarily they use recursion. You should be probably pretty familiar at this point with them from project 1. And I would also be familiar with breadth first search, which uses a queue. It's always also known as a level order traversal. So yeah, I would make sure to freshen up on all of that. And for poll questions for you all, I haven't figured out an effective way to do poll questions in person, but I guess just write down your answer, internalize like what would you answer. So what is the third node to be printed out in a post-order traversal of this tree? And whenever I'm doing like a traversal, I like to write it down on paper and be able to like visually see like how the steps are going. There was that diagram before of like the position of the drawing, and you can do that, but I prefer just to remember the left right node for the post order traversal, where the node itself is the last thing to be visited. So yeah, I'll give you all maybe like 10 more seconds to figure out this problem. Also, how's the speed for you all? Is it like too quick? Am I breezing through? There's a lot to cover, so sorry if like they're like it's quick, but if you have any questions, please like raise your hand. So the answer here is, in fact, if this would, okay, it is D. And you can see that from in the post-order traversal, we visit the left subtree, then the right subtree, then the node itself. So we go all the way down to 1, which is the leftmost node. Then we go back up to 3 and we visit its right subtree. We're at 6, we visit its left subtree, which is 4. And then we visit 6 right subtree, which is 7. So 7 is the third node to be printed out in this post-order traversal. Any questions? Oh, and yeah, that you can see the different traversals there. Once again, if you have a binary search tree, the in-order traversal for that will be a sorted list ascendingly. For binary search tree operations, there's search, insert, and removal, like all of our data structures, essentially, although some don't support searching through all of the elements. But the average time complexity is O of log n. However, the worst case time complexity is O of n. And that's true for all binary search tree operations, the insert, the removal, and the searching. And to reduce the worst case time complexity, we use balanced trees. So any questions about that? I mean, these slides are mostly for your review. So if you want to know like how the pseudocode is written for that or the code, you can look at these. Oh, yes.
Can you just explain why the average is log n?
Yeah, the average case is log n because most of the time we won't have a fully unbalanced tree. And so like the average case is a somewhat balanced tree in a binary search tree. And so the average case to search or insert or remove within that tree is O of log n. The worst case is when you have that like all of it like on one side, it's completely unbalanced and you have to traverse through all of the nodes to get to the one that you're searching for, deleting, inserting. Does that help?
Yeah.
Okay. For our balanced trees, you all should be pretty familiar with ABL trees at this point, but they are a self-balancing binary search tree. I would remember the balance factor and the height being, or the balance factor being the height of the left subtree minus the height of the right subtree. And it stays balanced, so all of its primary operations, insertion, deletion, and searching are O of log n. And that's because it guarantees the height of the tree will be approximately log n. And the balance function, the balance factors are checked after each insertion and deletion. So if you're given a tree and it asks you, for example, oh, what node is unbalanced in this tree? It's always best, in my opinion, to start from like the bottom, the leaves, and then work your way back up and finding the balance factors of each node. I would also write out the tree on paper. So I think you can have up to like 4 pieces of paper that are blank for the test. So like I would write out the tree and do the balance factors like that and find the node that has a magnitude of 2 or more. And that first node that has a magnitude of 2 or more is the unbalanced node. You can have, you know, possibly a node farther up the tree that is also unbalanced, but by correcting the unbalanced, like the first unbalanced node, the like one lowest down, you can fix that imbalance with usually just one rotation, or like, you know, the left rotation, right rotation, left right rotation, right left rotation. So what will be the root of the ABL tree after you insert 5? So we insert 5 like a normal binary search tree, and then node 10 is the imbalanced one. And we find that by checking all of the balances of the nodes in the tree and seeing that that is the first or the first one to have a magnitude greater than or equal to 2. And so going on to this poll question, after the rotation, what will be the new root? So to answer this question, we need to identify what type of rotation we need. If you remember the chart that I believe is in one of the slides, you can determine what sort of imbalance we have. And then after the rotation, where will 8 be in relation to the new root? So yeah, I'll give you all maybe 15 seconds to think about this. Are there any questions about ABL trees, the rotations, balance factor? Okay, maybe like 5-10 more seconds. I'll start explaining, but this is a left imbalance. So you have a left case, and so to correct that, you need to perform a right rotation, where 6 will be the new root, and we see that 10 is going to be made 6's right child. So in order to maintain the binary search tree property and to keep the tree balanced, you have to make 8 the left child of 10. So we do that right rotation, and then 8 becomes the root's right left grandchild. Any questions about that? Okay, so for red-black trees, we haven't talked about maps, I don't think yet, but I think your project is using maps. And so ordered maps are usually implemented using a self-balancing binary search tree, like a red-black tree, because we want that map to be ordered to some extent. So that's why C++ uses a red-black tree. And it's very important to know all of these rules. So for the 4 rules are: a node is either red or black, the root is always black, a red node always has black children, and from that you can derive multiple other facts. And it's also good to note that null references are considered to refer to black nodes. And then the number of black nodes in any path from the root to a leaf is the same. So yes, red-black trees are on the exam. However, you won't have to like code them. You just need to know them conceptually. So just remember the rules. Yeah, exactly, Francisco. Any questions? If you don't have any questions, I have several questions for you. Oh, does someone have a question? No, I guess not. All right, so these are true false questions about the rules of a red-black tree. So which ones are true, which ones are false on here? So I'll give you all maybe 5 more seconds to think about this. I'll start. I don't think we have any true false questions on the test. I mean, I looked at it, I just don't remember any true false. There's a mix of multiple choice, free response, and then like sort of like I can't say exactly what the example of this would be, but imagine that you have like an input box, and then you have to like put in the answer, and it's going to be like a single line answer. And that's like the 3 types of questions. So, yeah, why is this not going? Okay, so red black trees are self-balancing binary search trees. They do have, a node does have one color, so it's either red or black, but the color can be reassigned. So the color of the nodes is changed when there's a rebalancing. And the number of red nodes from any path from root to leaf is always the same. That's false because it's black nodes instead of red nodes. Does someone have a question? I think someone's unmuted. Feel free to raise your hand or unmute if you have any questions. Going on to B trees. B trees are also self-balancing binary search, or not binary, they're in-area trees. And they are good for large amounts of data. B trees have key value pairs in a node, and these are sorted ascendingly by their keys. So the important properties of a B tree are that all nodes have at most n children. The root is either a leaf or it has 2 to n children. Internal or non-leaf nodes have, like, rounding up n divided by 2 to n children. And then non-leaf or internal nodes have a maximum of n-1 keys. And then L is the maximum number of keys / items a leaf node, that should be added there, a leaf node can have. So in this tree here, for example, you can see that it appears that L is equal to 3 and N is also equal to 3, but they don't have to be the same. Although I think for the majority of the examples that we've shown, they are the same. A B plus tree is similar to a B tree, except for each non-leaf node contains only keys. So there aren't any key value pairs. And all of the data is stored in the leaves. So if any of the data appears in the non-leaf nodes, then that data is also repeated in the leaves of the tree. And the bottom layer, the leaves, are linked together, sort of like a linked list sorts. And yeah, any questions before we go on to the poll question? I know that B trees and B plus trees are a bit difficult. I would know how to do them. So you're presented with a perfect B tree with n equal to 3 and L equal to 3 and a height of 2, where it has level 0, where the root is, levels 1, and then level 2. And how many unique keys are in this tree? So you might recognize this question from previous poll questions. But in this time, I've improved it a little bit by adding a formula that you can use to solve this without drawing it out manually. And you can sort of derive that formula by looking at the examples. So I'm gonna go on, since we've already seen this question previously. It is 35 unique keys, and you can see that the root level 0, has one node with 2 keys, and so those are 2 unique keys. And you can see that n, so like 3 to the power of the level, which is 0 in this case, multiplied by n-1 is what we can use to derive the value or the number of unique keys in a B tree for non-leaf nodes. And then we continue that pattern for the level 1. And then when we get to the leaf level, which is level 2, we have n to the power of the height number of nodes times the value L, which is the maximum number of keys a leaf node can have. So doing that example visually, you can see you have 2 keys, then 6 keys on that level, and then we have n to the power of the height, which is 2, so 9 nodes, and each of them have L keys. So that's 27 keys in that bottom layer. And so when you sum that together, you get 35. That's different, but yeah, let me start this next. I don't think this is a poll question. Question 5. Yeah, this is not a poll question. So this would change because in a B plus tree, we only have unique keys, like all the keys are stored in the leaves. And I'll answer your questions in a second. So only the leaf level has keys that all of the internal nodes keys are repeated in the leaves. And so there is n, which is 3 to the power of the height, which is 2 times L, which is 3. So 3 to the power of 2 is 9. 9 times 3 is equal to 27. And it's useful to know this formula or know how to derive this formula. So yeah. And for your questions, why do the upper levels only have 2 keys? And the reason why is that they can have only n-1 keys. So that's the D rule there. And the reason why that is because we need n-1 keys to split the children. So if we go back to example of a picture, you can see that we need, for this node here, we need 15 and 18. So all of the values that are less than 15 are in the first child. Everything that's between the first and second key is in the second child, and then everything that's greater than the second key is in the third child. And that's why we need n-1 keys. Hope that made sense. Let me know if it didn't. Otherwise, I'll keep on going. For splay trees, they are also self-balancing binary search trees. And after a node is accessed, it moves to become the root via the zigzag rotations. And this ensures that the most commonly accessed nodes are the closest to the root and have the least access time. So, for example, getting like, if you search for a node that is not the root node, the first time you do that, it is O of n in the worst case, is you have to bring it all the way from the bottom all the way to become the root. And then the second time you search, it's O of 1. So in this splay tree, what was the Alexia asked, do we need to memorize the types of zigzag rotations? And I think that they're good to know. That's all I'll say. I don't know if, like, in the exam study guide, if it says zigzag rotations, then you need to know.
I think you put up the wrong question.
I am on the wrong question. Thank you. So what was the last node that was accessed in this split tree? But yeah, I would make sure that you review all of the material that's in the Exam1 study guide, or at least topics, I think, that are in the study. I don't know if it's called study guide, it might just be Exam1 topics. And so I would know all that. If we have time, I can search for it and show it to you all. All right, well, looks like you guys are getting it. It's 5. And the reason why that is because it's the root. So it was the last node to be accessed in this split tree. Any questions? That ends like the tree and balance tree portion. Although you could consider like a binary heap to be a form of tree. Okay. So heaps are a form of priority queue, and a priority queue is a special type of queue where elements have a certain priority, and elements with higher priority are dequeued before elements with lower priority. And if two elements have the same priority, they are served according to the order in which they were added to the queue. So it supports the following functions like insert, peak the highest priority, and pop the highest priority. And having a binary heap is a complete binary tree that satisfies the heap ordering property. So when you're referencing a node in a binary heap, either all of its children are of a less priority than it, or less than it or greater than it. And those are known as max heaps or min heaps, respectively. And so the smallest element in a min heap is the root. The largest element in a max heap is the root. And only the root can be removed. So the binary heap ensures O of 1 extraction of the element with the highest priority, whatever you're using to determine the highest priority. And this is an example of a data structure that doesn't have like O of login, O of login searching. Like it doesn't usually support like searching through the heap. But the insertion and deletion aspects of it are O of login. So when you extract something, it is O of login, because you then have to perform the heapify algorithm to determine what the new root will be of that tree, or that binary heap, sorry. And the node is inserted at the end of the heap, and then it is heapified up. So that's also O of login. Here are some visual examples of a min heap and max heap. And binary heaps are usually represented as an array, and this ensures that we can access insert something as like, I'll say like amortized time complexity of O of login. Because sometimes when you insert something, you will have to increase the size of the, like maybe double the size of the array. And that's like a possibility that happens only once in a while, or rather after like n divided by 2 insertions. And so when you average out like, oh, we have an O of n insertion every once in a while, and then every other insertion for the next n divided by 2 times is O of login. When you like average that out, that is O of login. And that's known as amortized time complexity, but I don't think you need to know that for your test. Sorry to introduce that.
Isn't
yeah.
isn't the parent supposed to be the floor of I minus 1 divided by 2?
Yes, yeah, it does. It is the floor of I minus 1 divided by 2. So yeah, that's a good point. So like normally you're using like an int if you're representing the index, and so like Java and C++ and stuff will automatically round down for you. But if you're using a language like Python, you need to make sure to like make it an integer so that it rounds down, like because Python, I'm not even gonna go into Python. So yeah, I would make sure to know, like definitely know like how to find the left child and the right child with the formula of 2 times the index plus 1 to find the left child, the right child being 2 times the index plus 2, and then the parent being at the floor of I minus 1 divided by 2. So any questions about this? Okay, so what is the array representation of the following heap? Is there an option to restart this, relaunch it? Yes. So for this question, looks like you guys are answering it. So the array representation is starting at the root, that's at index 0, and then you go left to right, level by level, and that's how you generate the array representation of it. So the answer is 80A. And this, like you could do that like in code if you were given like a binary tree and you're asked to like create the heap representation of that complete binary tree. You could perform a level order traversal using a queue and go left to right and add the elements in. So yeah, and then in the insert operation on a heap, where is the newly inserted node? Or where is the new node initially inserted? Okay, so it is the next bottom right leaf. I couldn't really think of a better way to like phrase that
It's
without giving you the answer.
technically at the end of the array would probably be a better way
Yeah.
to phrase that.
Yeah, at the end of the array. And I mean, technically the array and the heap do not have to match up in size. So like when you implement the heap, you want to internally keep track of the size of the heap, because sometimes when you delete something, you don't reallocate the array. You just move where you consider the heap to start, or I guess rather end. You move it. And so it's not always the end of the array. It's the end of wherever you consider the heap ending. And here's an example of heap insertion. I should mention that this code does not, oh, it got formatted here. Oh, that's not fun. Well, this pseudocode does not do like the doubling of the array, like you might see when you're actually implementing it, but this is just like more general pseudocode. So first, you want to check the edge case where the heap size is equal to 0. And if so, then we want to assign the first value to be the inserted value, and then we increment the size of the heap. And then we return. If it's not the edge case, then we want to insert the value at the end of where we consider the heap starting, and then we will increment the heap size. And then we perform the percolate up or heapify up algorithm. And yeah, so we insert 1 at the end here, and it's at the end of the area that we consider as part of the heap. And then in our percolate up function, we find the parent index, and this will automatically floor this operation just because it's an int. And we check if the heap, the child value is less than the parent value, then we swap the child and the parent, and then we perform heap percolate up again. If the child is greater than the parent, then that satisfies the heap ordering property for a min heap, and we don't swap. And then we swap them, and then we check 1 and 5 against each other, and we see that 1 is indeed less than 5, and so we swap them and we percolate up. Sorry that these slides are a little bit weird. I downloaded them, but yeah. And then, yeah, the heap insertion is done. Well, it will be called again, but the parent index is going to be child minus 1. So the child is at index 0, and 0 minus 1 is -1. -1 divided by 2 is brought to 0 in C++. Yes.
Can you write something like swap on your pseudocode on the exam?
Yes. Yeah, you can write like swap. It's like that's like one of those operations where we know you know how to do it. It's like you have to create a temp and then you have to like swap them. So yeah, just write swap. Ooh, I just revealed the answer. All right, well, in the delete operation on a heap, the root node is always deleted. And we don't actually like free the memory, we just overwrite it with the value that is at the end of what we consider to be the heap. And here the heap size is not 0, so we return. And then we overwrite the root of the heap with the thing at the end, which is 12. And then we decrement the heap size and we percolate down, which can also be called bubble down or heapify down. And we give the index of the parent, and we check the left, we find the index of the left and right child, and then we check if the right child is within the heap and the heap and the heap's the heap's right child is greater than the heap at the parent's index at this point, then we assign the max index to be the right child's index. This is a max heap deletion, by the way. And then after that, we check if the left, well, if at this point we know like if the right child is then the left child also exists within the heap. And then the heap's left child, if it's greater than the parent, then we set the, actually, this is not complete pseudocode. Sorry about that. You would also need to check that it is, sorry. We check the heap max index. So that could be either the right child or the parent. Sorry about the confusion there. And so in this case, the greatest of 12 children is 45, or the left child. And so we swap the values because max index is not equal to parent. And so we swap those values and then we percolate down again. And then we perform it for the next set of values. So once again, we check the 12 against its left and right children. And we see that 12 is in fact greater than both of its children. And we do not swap them because the max index is equal to the parent. So yeah, this code is pretty general for, well, you can apply it to both min and max heaps. The percolate down function, all you have to do really is swap the signs. So this is the, make sure I'm saying which one it is. If the right child is greater than the max index, then you swap it. Okay, so this is the max heap one because we're checking if the child is greater than the parent, then we want to assign the max index. And similarly for heap insertion, for the insert node, this is the same for min heaps and max heaps. And then this code is also just swapping the signs. But yeah, did that make sense to everyone? You know, the pseudocode's in here for a reason. And yeah, so for heap performance, sorry for leaving the poll up. Oh, that's the wrong question. Question 9. What is the worst time complexity of adding / deleting an element to / from a binary heap, I should say. Okay, it is O of log n. Putting. And for the heap performance of if you have an array of in elements, what would be the time complexity of building a heap based on inserting all the in elements of the array into a new heap? So let's say you have an unsorted array, and then you want to make it a heap. So you start inserting those elements into the heap. And I'll give you maybe like 5-10 more seconds on this. And this is our last slide, I'm pretty sure. So if you all have any questions after this, let me know. And the answer is in log n because you perform in insertions, and those insertions are in the worst case log n. So anything you all want me to review from the slides or just in general? I can find the study guide. This is a bit risky. I don't know if there's something potentially not good to show, so I'm going to move this over here. But yeah, think of any questions that you might have. While I look for the exam topics and expectations. There it is. All right. So you can see the point breakdown here. The exam is up to heaps. That is correct. Can you go over question 5 of quiz 4? Yeah, I can do that in a moment. First, this is in the files under exams. And yeah, this just tells you everything that you need to know. Someone asked about zigzag rotations and splay trees, and it does say types of rotations here. So yeah, and for the balanced trees here, you don't need to know any of the pseudocode for it, but as you can see here, you need to know the pseudocode for heaps. And yeah, you want to know the traversals, performance. Yeah, you'll probably see a couple of questions like we had, like what's the time complexity in the worst case for XYZ operation or this snippet of code. But can you show how so with B+ trees and insertion, oof, I'm gonna direct you to like Google or YouTube, because that's dirty. I don't like B+ tree. I'm not prepared to show it. Sorry, if you really want me to explain it, you can message me, or actually I'll just put it on the Slack channel, on the all other questions Slack channel, I think. But yeah, for question 5 of quiz 4. Oh, any questions out here, general audience? Quiz 4, question 5, is that correct? Yeah, quiz 4, question 5. So go to that. Oh yes, I created this question, so sorry about that. So this question is with an in-array tree, and we ask you to essentially identify all the valid permutations of a depth first search algorithm on this ternary tree, where there isn't any inherent ordering for like the left right node. So when you have a depth first search, you visit an entire subtree before you go on to the next one. So you can see that 1 through 4, this is not a depth first search because we visit 4 before we complete visiting child 3's subtree. 1, 2, 5, 9, that's we complete visiting that subtree. 3, 6, 7, we complete visiting that subtree, and 4, 8. So that is a valid permutation. Then 1, 4, 3, that's not a valid permutation because we would visit 8 before we would visit 3. We have 1, 4, 8, 3, 7, 6, and 2, 5, 9. That is a valid permutation. 1, 3, 6, 7, 2, 4. Oh, 2, 4. That's not correct because we haven't finished visiting 2 subtree there, so that's not a valid permutation. Then there's 1, 4, 8, 2, 5, 9, and 3, 7, 6. And so that's also a valid permutation. So we have the 3 possible permutations of this unsorted ternary tree. So did that answer your question? That's a breadth first search. So yeah, breadth first search uses a queue, it visits every level. Depth first search is like an in order, post order, pre-order, traversal. I did that totally out of order. Pre-order, in order, post order, traversal. So yeah, any questions? Oh, did you have a question? Or maybe no. Okay. Well, we're out of time. So if you have any more questions, you can direct them to the Slack. I will take a note of, let me see, B plus insertion. Get to that on Slack. And I'm trying to think. Yeah, if there were any more questions that you had or I was not able to answer during this session, please send me a message on Slack and I'll post an explanation in the all other questions channel. But yeah, thank you all for attending and see you next week. Good luck on the exam.